Good morning, afternoon, or evening. I am sad to say this will be our last lesson of the year. So I just want to say thank you for a great year. Today we're going to talk about Trig Part 3, and we're just going to look at some very important right triangle trigonometric applications. If you remember, I told you that trig was really, really important because it's used a lot, almost daily. Today we're going to look at some examples of word problems, real-life applications of how this is used in our daily life. And before we go into the word problems, I have to explain to you angle of elevation and angle of depression. This is a huge part of trigonometry and a very big part of the ACT. You're going to see stuff like this, and you're also going to see this next year and the year after. So let's focus and learn how to do this right now. Okay, angle of elevation, guys. If you notice, you have this little guy over here. Okay, he's called or she's called the observer. And the observer, you got to picture the observer as yourself looking straight ahead, just shoulders straight, literally. You're just looking straight ahead. Okay, that straight ahead, that's your baseline. So the baseline is when you're just looking completely forward, straight, you're just looking ahead. All right? Now, you see a plane in the sky, what do? Don't you tilt your neck up and look up? Okay, that tilting up of the neck, that makes your line of sight go up. That's your line of sight. Since I went up from my baseline, my friends, this is an angle of elevation. Think about it like this. I know it's simple, and you might think, oh my God, why is he making it so baby? But so you can really understand, you elevated your head. You looked up. It's literally that simple. That's my angle of elevation. What am I looking up to? I'm looking up to an object. Okay? Does that make sense? All right. Now, angle of depression. Okay? Any outdoor enthusiasts, anyone who's ever climbed a mountain or a hill, has done what this gentleman has done right here in this picture. In this particular case, the dude is still looking straight, or the dudette, doesn't matter, female or male. And I'm looking, it doesn't matter how high on a mountain I am or how low in a valley I am, it doesn't matter where I am. I'm looking straight ahead. That is my baseline. Again, the baseline is where the observer is just looking straight ahead. In this particular case, the observer sees an object down here. So, of course, if you're up on a mountain, you've got to tilt your head downwards. You have to depress your head. That is an angle of depression. You're looking down, so your line of sight looks down to catch your object. Does this concept make sense, guys? It's pretty simple, right? Okay. Let's show you how to apply it, because that's it. That's the only thing new that we have. Okay. From an observer on the ground, the aerial run in Snowbird, Utah, which, by the way, this is the aerial run in Snowbird, Utah, has an angle of elevation of 20.2 degrees. Its vertical drop is 2,900 feet. Find the length of this run. So, you've got an observer right here. Okay? You've got an observer right there. And from an observer on the ground, the aerial run in Snowbird has an angle of elevation of 20.2 degrees. So, my baseline, okay, was here. Right? He's looking up at the mountain, and that's got an angle of elevation of 20.2 degrees. Why? Because it said from an observer on the ground. So I'm here on the ground, I'm looking up. That angle is 20.2 degrees. Yes, sir. The baseline could go this way or this way, son, but if it went that way, then the angle would be 20.2 here. Doesn't really matter. You could look at it from the left or the right. Thank you, sir. Now, It says the vertical drop is 2,900 feet. That's in most brochures. So I just created a right triangle, guys. And that's 2,900 feet. I want to know how long is the run? How long is the run, the hypotenuse? So from my 20.2, what is the side that has 2,900? That's my opposite. Very good. And the run itself would be the hypotenuse. Okay, guys, you're done. Who uses opposite and hypotenuse, gentlemen? So the sine of 20.2 degrees equals opposite over hypotenuse x. That's my run. Multiply x to both sides. So I've got x times the sine of 20.2 degrees equals 2,900. Sorry, I got a little messy there. Divided by the sine of 20.2 degrees, sine of 20.2 degrees. So x equals 2,900 divided by the sine of 20.2 degrees. And could you please give me that answer? 8,398.4, and this is 0.54. Sorry, thank you. 0.54 feet. And that makes sense. It's a nice long run. It's a little bit over a mile. So it's a nice run. Sir. In this particular case, they gave you the degrees. Okay, what are you asking then? Okay, how did he figure out the 20.2 degrees? There's a little, it's called a clinometer, and it's basically a protractor with a little looking glass through it. You can make one on your own. If you get a protractor, you put a straw on the bottom of it, okay, and you hang it so that it can go up and down, and you attach it to something still. As you go up or down, the protractor will move along with your movements, and then you can figure out that angle, okay? Thank you so much. Does that make sense? All right, let's move on. Now, no more aids. We're going to have to actually draw it all out ourselves. At a point on the ground 40 feet from the foot of a tree, the angle of elevation to the top of the tree is 42 degrees. Find the height of the tree to the nearest tenth of a foot. Okay, so what we got here is Mr. Tree. Okay, and at a point on the ground 40 feet from the tree. So 40 feet from the tree, the angle of elevation to the top of the tree is 42. So my observer's here. He's got to look, or she's got to look up. So that's the angle of elevation, which is 42 degrees. They want to find the height of the tree. Guess what? This is how they measure buildings, mountains, trees, valleys, canyons. No one's going to climb up that tree with a tape measure. Seriously. I mean, I know it sounds funny, but you're not going to do that. It's math. So, from the 42, what is the height? What side is that? Opposite. Phenomenal. What is the 40? Adjacent. Phenomenal. Who uses opposite and adjacent? Tangent. So, a tangent of 42 degrees equals opposite over adjacent. Tangent of 42 times 40 would equal, that's going to equal 36 point, no, to the nearest foot, so 36 feet. It's 36.01, but to the nearest foot, so it's 36 feet tall. Perfect. Beautiful. Amazing. Does that make sense, gentlemen? This is real life. If you're asking, Mr. Morrow, what person is going to go out and just randomly say, you know what? I want to find the height of that tree. Perhaps a logger, people that cut trees down for a living, a paper mill factory, A paper mill factory would want to probably go after the tallest, biggest trees. They're not just going to look at it and go, gee, I think that one's it. They're going to actually calculate it. Why do they calculate it? Because I'm sure they have a formula that tells them every foot of tree gives me this much paper. So just one little tiny example of why this would be very useful. Number 3, find to the nearest degree the angle of elevation of the sun when the vertical post 15 feet high casts a shadow which is 20 feet long. So I've got this vertical post and it's 15 feet tall. The sun is over here. Horribly ugly sun. Okay, that's the sun, I think. It casts a shadow that is 20 feet long. I can connect these two dots, making a hypotenuse. I want to find the angle of elevation, okay? So we're looking at from here, I'm looking up to catch this sun, so that's my x degrees or theta. From my x degrees or theta, what is the side 15 called? From the angle theta, what is my 20 feet called? Excellent. Who uses opposite or adjacent? Tangent. So tangent inverse, correct? Because I want to find an angle, equals opposite over adjacent. So inverse tangent, sorry. Inverse tangent. Oh, come on, man. Hold on, my calculator is giving me, here we go. Inverse tangent of 15 divided by 20 equals 36 to the nearest degree, 0.8, so 37 degrees. Does this make sense, guys? Okay, may I continue? Okay. An observer in a balloon, okay, which is 22 feet, which is 2,000 feet above an airport. So there's this airport here on the ground, and you have an observer up here in a balloon, which is 2,000 feet above an airport. Finds that the angle of depression of the steamer ship out at sea, so there's a steamer ship out at sea right here, out at sea is 21 degrees. Find to the nearest 100 feet the distance between the observer and the balloon. I'm sorry, the observer in the balloon and the steamer ship at sea. So he wants to know this right here, the distance between them. Okay? Now, I want you to pay attention to this. Yes, sir.
Since it's the distance between the balloon and the steamer ship, would it be the hypotenuse, not the opposite?
Okay, the distance between the balloon and, okay, the balloon is here, right?
Yeah, but if it's a direct line with the
And this guy's here, right?
yeah.
So the distance between them would be from here to here. I should have specified. You know what? I'll take that into consideration. I should have specified what is the horizontal distance. Is that better? I can see what you're saying, because it could be the distance from this hypotenuse, or it could be the x distance. So if I say horizontal distance, it's horizontal. Thank you so much. Does that help? Okay, now, I want you to pay attention to this, though, guys. How many people think that this angle here is 21 degrees because it's an angle of depression? Right? Okay, wrong. Let me show you. I do this on purpose. When the guys or the ladies on the balloon, isn't this a baseline? So, when he or she looks down, this is the 21 degrees, correct? Do you see that? You guys with me there? What's the total degree of this right here? 90. So if that's 21, what is this angle right here? No, 89. 79. Come on, guys. 90 minus 21. 69 degrees. Very good. So now I have my angle. From this angle, what is this horizontal distance? Opposite. And what is this guy? Adjacent. So who am I using? Tangent of 69 degrees equals opposite over adjacent. So the tangent of 69 times 2,000 equals 5,210.18 feet. It's almost a mile away. Does that make sense, gentlemen? Sir? The hypotenuse is this. So then why are you asking me? No, I'm just kidding, but I mean, if you know that, then yes, that's the hypotenuse. Sir?
Could you use the baseline and made a triangle on top there?
Okay, the question was, could I have made a triangle here and still found this distance? Yes, absolutely. Because this is still going to be 2,000. It's just all a matter of perspective, how you want to look at it. Phenomenal. Are we good here, guys? Okay. Next. From the top of a lighthouse, 160 feet high. So I have this lighthouse here. Okay. And it's 160 feet high. The angle of depression of a boat out at sea is 24 degrees. Find to the nearest foot the distance from the boat to the foot of the lighthouse. So that's a lot more clear than what I put before. Remember that the base of the lighthouse is at sea level. So here's the sea. And please do not steal this drawing because it's in museums. So if you steal that, I'm going to have to sue you for copyright infringement. Please try to pay attention to the math. I know that boat is amazing, and very few people can draw that well. But okay, so now the lighthouse has a baseline. Remember here, guys, it has an angle of depression to the boat, 24. Please remember that goes down from the baseline, so that's 24 degrees. So if that's 24, 90 minus 24, this is 66 degrees. I want to find x, the distance from the boat to the base of my lighthouse. And again, in this case, I'm going to use what is the x, what is side x from 66? That is my opposite. And what is my height from 66? Adjacent. Who am I going to use? Tangent. Tangent is 66 degrees equals opposite over adjacent. Go ahead and calculate it, guys. What's tangent of 66 times 160? Tangent of 66 times 160 would equal 359.4. But I want this, yeah, I didn't specify to the nearest foot or anything. Yeah, so feet. There it is. Does that make sense? Yes, sir. Yes, sir. Yes, yes, sir. The question was, when we're talking about angle of depressions, do I always have to make a top baseline here? Yes, because that's your baseline, and then my angle of depression goes this way. Okay, so that's my angle of depression. And then since all of this is 90, it's 90 minus the angle of depression gives you the angle that you're going to work with. Always. A lot of times, people really mess up because they do this. Whatever, let's say you're at the top of a mountain, and they say that you see whatever, an object here that you're fascinated with. They say, oh, The angle of depression is 48. People do this all the time. That's wrong. That is wrong. Okay? The angle of depression is 48. Great. That's my baseline. That's 48. You got to subtract 90 from that. That's 52. Does that make sense? Thank you. Okay. Let us continue, guys. Come again? What? What did I do? Wait, now I'm curious. What did I do? Ah, 42. Okay, it does matter. It does matter. If you're going to correct me, correct me. Don't be ashamed. That's my job, to be corrected sometimes if I have to. Okay. Thank you, guys. Let's do it. On airplane which had, oh, this is a really good one. On airplane which had taken off from an airport, traveled a ground distance of 3,660 feet. Okay? What is the angle of elevation from the point of takeoff to the point when the plane has traveled 4,150 feet through the air, round to the nearest degree? Okay, so you had this plane, okay, and it took off from an airport and traveled a ground distance of 3,660 feet. So basically, the plane took off, right? It took off, right? But as it's taking off, it's going a horizontal distance as well, correct? So the distance as it was taken off that it had on the ground was 350. That does not mean that it was rolling on the ground. That means it took off. And as it took off, not only am I going up, but I'm also moving to the right, correct? You guys see this? Okay. What is the angle of elevation from the point of takeoff, that's right here, that would be your observer, to the point when the plane has traveled 4,100 feet through the air? Is that the height? No. That's this. So I want to find this theta right here. And thank you very much. You have to use the inverse cosine. From this theta, this is the adjacent. From the cosine, this is the hypotenuse. Great. So cosine inverse of theta is going to equal cosine inverse of adjacent over hypotenuse. So inverse cosine, inverse cosine of adjacent over hypotenuse equals 28.1 degrees to the nearest degree, 28 degrees. Does that make sense? We did a lot of good word problems here today. See how easy they were? Because you learned already the basics. I'm very proud of you guys. Okay, that's it. And that's it. Okay, excellent. Guys, thank you for a wonderful year. I hope you learned a lot. And have a good day.